can't remind you.
Okay, and yeah, now we wait 2 minutes for them to actually set up the same.
Sounds good.
So now we would like to disconnect. Yeah. It's also like 30 seconds delay because I could see myself. Yeah, which is expected. We still recorded onto this, so it's oh yes, that's exactly why. We'll detect the block. It's like you're not allowed to stream onto our platform because we know this content is not yet approved.
Okay, well, let's hope Google's not contracting with our.
But yes, I'm going to now reply to the people who are asking where the link was for the actual link. Be like, hi, now here it is. We missed the first talk. It's still recorded. We don't have like I don't know if you remember that guy. The announcements they're live. Yes. Voice name from the beginning. Yeah. And goodness, they also don't post them live anyway, so we can record it, so we'll still get it out faster than yeah, we also need to yeah. I guess we can start. Yeah. Okay, thanks for waiting. Our next speaker is Paul Holland from Argonne, who is going to talk about 30 years of differentiating parallel programs.
Okay. Thanks a lot for the introduction, and thanks for the opportunity to talk. So I'm going to start off and explain why 30 years, then spend a fair amount of time sort of rehashing my PhD thesis and the various topics that I looked at in my PhD thesis, and then spend the rest of the talk talking about all the things that I didn't address in my PhD thesis, and hopefully that's the more interesting part of the talk. So in the beginning, so why 30 years? So as far as I know, the earliest work on applying automatic differentiation to parallel programs was this master's thesis from Ruth Hinkins, published in 1994. So we're not quite at 30 years. I guess the actual publication was in September of 1994, but we're pretty darn close to 30 years. So here's the abstract from this report. Looks at applying automatic differentiation to networks of workstations using PVM, MassPar using MP4tran, and a CM5 using CM4tran. Get speed ups of up to 8.7. That probably sounds pretty modest by today's standards, but you have to remember these parallel systems were not that big. Many of them only had about 8 or 16 nodes. So again, as far as I know, this is the earliest application of automatic differentiation to parallel programs. It supported a variety of different parallel programming models, one of which came from Thinking Machines, which, for those who don't know, was right up the road here. I guess they started in Waltham and then moved back to Cambridge. But It was an MIT spinoff. This was an elemental tool according to the David Judas taxonomy. The user had to replace all elementary operations with subroutine calls. So every place in your program that you had an addition, you had to replace that with a subroutine call to add, or whatever it was called, and every time you had a multiplication, you had to replace that with a subroutine call. So it was a little bit hard to use. There were, for many of these tools, sort of supplementary tools to try to support that process and make it a little easier for the user. But it was sort of a very basic level of automatic differentiation. This paper was not the first to look at AD and parallelism in concert with one another. There was work in 1987 by Lawrence Dixon looking at how to parallelize forward mode AD. There was work in 91 by Christian Bischoff looking at parallelizing reverse mode AD at a very fine granularity. And there was lots of other work in between and after that. And I'm not going to talk about any of this work on exploiting the parallelism that is introduced by automatic differentiation or parallelizing the derivative computation itself. That would be a completely different talk. So what was my PhD thesis about? So who here has read my PhD thesis? No one. Perfect. So I can tell you anything about what was in it. Of course, it's on the web, so you can fact check me later. This looked at extending the work of Hinkins to look at source transformation, efficiency, and MPI. I was writing the thesis at the time that the Adafor tool was still kind of new and exciting, and so we were looking at how can we take tools like Adafor and adapt them so that they can be applied to parallel programs, especially parallel programs implemented with MPI. MPI was also brand spanking new at that time. So these are the chapters in my thesis. There was an introduction and some discussion of how you build tools for automatic differentiation with a focus on source transformation tools. And then the meat of the thesis was looking at ensuring correctness in the derivative code, producing efficient derivative code, and some new issues that sort of come up in the context of distributed memory parallel programming that maybe don't show up in sequential programs. And then a little bit about the tools that were developed or the extensions to Adafor and Adac that were developed, and then some applications of the work. And then finish up with some other issues, which was really looking at some alternative parallel programming models and some other issues that the thesis didn't get into. Okay, so correctness. At the time, there was a lot of discussion about whether you want to associate derivatives with a variable by name, have two different variables that are somehow mapped to one another by name, or to do association by address, either by having a mapping from the address of a variable or sort of bundling the variable and its derivative together in a single data structure. And then there's a sort of related issue when you start looking at this in the context of message passing programming models, which is, are we going to send two messages or one message? And so, at the time, the final verdict was that association by address and using MPI-derived data types is likely to be your most efficient option. Unfortunately, tools like Adafor and I guess Tapenade still today did association by name, and therefore you're left with choosing to do either MPI packing and unpacking or to send two messages. And at the time, the sort of power of the computers relative to the latency of the networks was very different from today. So there was actually a crossover point, but the crossover point was still when you were differentiating with respect to about 1,000 or so independent variables. If you were doing anything less than that, it was more efficient to do the packing and unpacking. Correctness also comes into play when you're dealing with non-smooth reductions. And so in particular, looking at the min and max reductions, they're not everywhere differentiable. Detecting the point of non-differentiability requires additional work. And so you can proceed with some sort of generalized gradient. And there's a few different choices. One is to let the derivative of y with respect to some xi equal 1 for arbitrary xi that is equal to the max or min. If you want to use that approach, then you can use the max-loc or min-loc reduction in order to identify one location where the maximum or minimum value occurs. But often you don't want that. Sometimes you want to share the derivative equally among all of the variables that are tied to be the max or the min. So you want them all to contribute equally. In that case, you need to know how many values are equal to the maximum or the minimum, and then do a summation over all of those values. And so that requires two phases, but sort of gives you the most generalized derivative, I guess. And then another choice is to use a user-defined reduction operation and handle the max and min operations locally. That's going to result in unequal weighting of the derivatives. And so if the reduction operation is implemented as, say, a binary tree, then when you have sort of two variables that have the same value, they're going to sort of split the derivative 50-50. And then when you encounter a third, it's going to get 50%, and the first two are going to get 25%. And so that's sort of not the optimal strategy if you care about equal weighting. So looking at efficiency, we looked at activity analysis. I think probably everyone here is familiar with activity analysis, but activity analysis was introduced, I think, in Adafruit, and does a domain-specific data flow analysis in order to identify the variables that lie on the computational path from the independent to dependent variables. Tools that were unaware of MPI semantics could yield incorrect activity analysis, and so a conservative strategy to induce the correct activity analysis is to induce a dependency from all of the sent variables to some global variable, and then from the global variable to all received variables. Turns out that's not actually conservative. It doesn't account for multiple processes, and so if your automatic differentiation tool doesn't know that there's sort of this implicit parallel for around everything, then it might miss a dependence that exists. So if you have a send in one branch of a conditional and a receive in the other branch of the conditional, your compiler is going to assume that you take one branch or the other, not both. And so you can get incorrect analysis that way. Michel Strout did work later to sort of extend data flow analysis to the MPI context. You can be a little bit more precise and replace that global variable with multiple global variables where the choice of global variable depends on the tag and the data type. Sorry, I can talk.
Switch to camera, maybe?
Yeah. Okay. Good? Yeah. Okay. So anyway, interface contraction, we're going to differentiate with respect to this smaller set of live variables, and then differentiate those variables with respect to the independent variables, apply the chain rule, and thus reduce the overall cost of the computation. If we're in a parallel program, then the number of live variables depends on whether the values are distributed or replicated, and so you need to take that into account. And then we also noted that the reduction operations provide a convenient location for looking for contractions in a parallel program. Sparsity is another way to improve the efficiency of a derivative computation, but it's typically managed via complex data structures, which requires some additional attention when they're communicated via messages. Reverse mode, my whole thesis, there's 2 paragraphs devoted to the reverse mode that basically say, reverse mode is just a extension of what has been done for forward mode. Sends become receives, receives become sends, end of story. That turned out to be a bit of an oversimplification. And then sort of finally, I looked at some new issues. So AD introduces some new parallelism. I mentioned that earlier, the work by Dixon and Bischoff. Which parallelism should we exploit? The conclusion is that almost always, if the original program to be differentiated has adequate parallelism, it's better to exploit that parallelism. The parallel efficiency will increase in almost every case. And so if you had good parallelism initially, you'll have even better parallelism in your derivative code. But if you didn't have good parallelism, then you might want to combine the original parallelism with the introduced parallelism in order to get greater scale out. Parallel reductions, I mentioned max and min already. Product reduction is kind of interesting. You can differentiate it using the forward mode, or you can differentiate it using the reverse mode. If you differentiate it using the reverse mode, it ends up looking like 2 calls to a parallel prefix computation, so that you're basically computing a parallel prefix from one side and a parallel suffix from the other side, and then combining the right prefix and suffix in order to have the product of every variable except the one you're differentiating with respect to. Later, we realized that you can actually modify the parallel prefix algorithm so that you can do just a single modified prefix computation in order to get that derivative directly, and you don't have to do sort of these 2 prefix operations. So I guess sort of already given away the fact that this is not the end of the story. I graduated in '97. I was real confident that I'd solved all the important problems, and then along comes Jean-Luc and Patrick Heimbach. We were doing some work with MIT on differentiating MIT GCM, and lo and behold, MIT GCM used non-blocking communication. And so this simple idea that send becomes receive and receive becomes send no longer applies in the context of non-blocking communication. One way of handling non-blocking communication is that your non-blocking receive becomes a wait, and a wait becomes a non-blocking send, and then a non-blocking send becomes a wait, and a wait becomes a non-blocking receive. That's great if you can actually figure out from your static analysis which weights go with which non-blocking operations, but in general that may not be possible, and so you can extend MBI to make it more readily adjoinable. And Michelle, I think, has some experience with doing that. One-sided communication is even harder, and I think it's still an unsolved problem in general. So I said that blocking was easy, and send becomes receive and receive becomes send. Even blocking isn't completely trivial, and this sort of statement that you can just sort of invert the receive and send really is only true for synchronous communication. You have to be a little bit careful with blocking. And I didn't really look at OpenMP that much. Shared memory parallelism, I thought, well, this is easy. There's nothing challenging about differentiating shared memory parallelism. And for forward mode, that's true. There's really not a lot complicated about applying automatic differentiation in the forward mode to shared memory parallelism. It kind of just goes along for the ride. In reverse mode, not so much. Reads become writes, writes become reads. We heard that in the first talk. And a parallelizable forward loop doesn't imply that the adjoint loop is parallelizable. And so I think Michael Foster's thesis is the one that first identified the conditions under which the adjoint loop could be parallelized, possibly with some additional safeguards. And so that sort of handles a few cases, but there are some more interesting cases. And so in subsequent years, I'll call them the Hickelheim years, Jan started looking at gather type operations and other types of more complicated computations in OpenMP. Looking at the case where if your per iteration read set is the same as your write set, then you can use the same parallelization strategy for the adjoint computation as you do during the forward computation. So this extends the set of parallelizable loops that can be differentiated. It's also the case that for many types of stencil-based computation, you can basically rip the stencil apart and then reassemble it and do a stencil type computation for the reverse computation. This is a lot easier in an array language than it is in imperative language like Fortran, but it can be done. And of course, there are all these nice corner cases that arise in OpenMP. So if your computation depends on the schedule, the assignment of iterations to threads, then you may need to keep track of what the schedule was. And you have private variables with an OpenMP, and so then you have scoping issues, and you have multiple copies of variables across iterations that you have to keep track of. And so Jan and Laurent Haskell explored a number of these challenges in applying reverse mode to OpenMP. And then there's GPUs. So for a long, long time, I'm not sure why such a long time, really there was no work on applying automatic differentiation to GPU parallelism. There was plenty of work on CPU parallelism. There was work on using GPUs to parallelize the derivative computation, but there really wasn't work on applying AD to CUDA code or HIP code or any other sort of parallel programming model targeting GPUs. And I can speculate on why that was the case. I know why I and my collaborators at Argonne didn't work on this, and it was really the absence of a single portable programming model for GPUs and the difficulty in developing a parser for one or more of these programming models. And so fortunately, a few years ago, Billy decided to do a practicum at Argonne. This was during the pandemic, so it was virtually at Argonne. And started working with us on applying Enzyme to parallel programs and working at the LLVM IR level. And so that allows one to handle all of the programming models that are supported by LLVM. And then more recently, extending that to deal with MPI programs, treating MPI as sort of an implicit parallel for and non-blocking communication as implicit tasks, which I think is very clever and elegant. So I don't think we're done yet. I don't know what's next, but I think there's probably still additional work to be done in applying automatic differentiation to parallel programming models. Maybe that will depend on what the parallel programming models of the future are, and maybe it comes down to other things that we may have overlooked so far. So I don't really have conclusions, other than that, when I finished my thesis, I was sort of woefully unprepared for all of the additional work that remained to be done. And I have some references to some of the papers I referred to over the course of the presentation. And I missed some, but hopefully I've covered most of the important ones in terms of applying automatic differentiation to MPI and OpenMP programs. So with that, I will take questions.
people any questions in the audience? You will have to repeat questions when somebody asks one. I can start with one pretty generic. Yeah.
This is not really a question. Okay, this is not really a question. But fun fact, since you sort of mentioned that a lot of this, it's like doing stuff from your thesis work, this room that we're actually in right now is the room that many people tend to defend their theses in. So it's funny enough and appropriate.
Good, I'm glad I'm not defending mine in front of all of you.
And so my question was connected to the previous talk. So we talked about like MPI and OpenMP and various parallel models and how possible but hard it was to do in Fortran. So do you see one thing we should have in a representation for AD that would make it simpler? Like in any compiled representation for AD to support parallelism that we could map onto somehow?
So the question, as I understand it, is there something that we should be adding to the AD representation to make it easier to differentiate parallel programs? And I can't think of anything that sort of wasn't already in sort of these last two papers by Billy et al. I think introducing sort of some of the fundamental concepts from parallel programs into the AD tool, makes it possible to handle a wide range. I don't know. Probably there are parallel programming models that are not implemented in LLVM. And therefore are maybe not well suited for differentiation using enzyme. But for the things that use enzyme, I think enzyme's pretty complete. Maybe Billy disagrees.
I mean, I think one thing, and ironically, Alex, this is possibly, prefaced by...
It's absolutely not a self-serving question.
Yeah, so some context as well. So Alex and I are also exploring, so Enzyme doesn't just work on the LVM IR representation, but recently Alex, I, and many others have been sort of exploring extending this to not just it's ironically coming out of the camera right now. So I am right next to the thing. So many of us have been recently exploring doing so on the MLI representation, which also has the sort of nice little caveat or premise that we can now imagine changing what the IR looks like. So we can imagine having like a parallel 4 as a native construct. And similarly, I think, and this goes back to actually what Dougal was saying is one of the places that we're sort of like having a native representation of this, hopefully going to explore next, of your original schedule that you had for your parallel program might have been good for your original parallel program, but your schedule may not be the best for the reverse pass. So one, the extent that we can sort of like look at combining with the schedule, but two, even sort of going past that, and this is actually what Martin and Jacob were looking at a lot recently, is like if we imagine in a sort of schedule agnostic form, where like this has not already been decided, we can sort of co-design the choice of the schedule, not just based off of, say, like the hardware availability or whatever else caches that's typically done, but also with the AD-specific knowledge that, hey, we're going to invert reads and writes, we may want to do this differently.
Yeah. That makes. You mentioned that, I think, at the Euro AD workshop as well. So, yeah, I think that's a really interesting direction.
Yeah, that's why I'm trying to get to the point. It's like we can define whatever representation we want, but now we have to define what is the ultimate differentiable programming abstraction, something. And here's like, okay, differentiable abstraction, but the way, okay, at least I tend to be more serial. Don't interrupt. I'm loud enough.
Yeah, so I mean, I think
we need to think in parallel terms, and we sometimes don't, and I guess we should.
Yeah, no, I think there's that. I think also sort of what Billy alluded to is a situation where sort of by default a lot of our imperative languages and our parallel programming models that are built on imperative languages tend to be very prescriptive sorry, I can stand where I'm supposed to.
It's
No,
not.
they tend to be very prescriptive, and I think what you'd like in order to facilitate differentiation is something that's a little bit more descriptive and leaves more up to the compiler to decide, how to implement things and how to rearrange things, and so. So I don't know how you sort of rip that prescriptiveness out of our favorite programming languages, but maybe that would be a good thing. Maybe you start over from scratch.
So ironically, my former advisor, or my advisor would probably suggest using a language he's worked on a lot, which has the nice sort of property that it's, rather than, like you say, being prescriptive, you have to run it, it's sort of descriptive that this can run in parallel but sort of serial. And I think to the extent that we can extend a lot of other programming models like that would be just beneficial even outside of AD for optimization, but also a non-trivial task to do by hand, and also something that is a non-trivial task for a compiler to find automatically. So there's a lot of interesting stuff there.
Okay, we are running out of time for this talk, so thank you, Paul. We'll have another 2-minute break, and we'll please the next speaker get on stage.
Can you pause?
Be forewarned, this tripod is a lot more fragile than the other tripod.
Yeah, it's okay. It just,
Can you switch to code?
Yeah, we just want to double check. Okay, that looks all solid.
That should be like 2.
I'm going to zoom out. Sorry. I'm just going to zoom out a smidge. There you go.
too much.
Yeah. So there.
It will hear you. If you move, you will get out of range.
Okay, so we are switching gears a bit from more of the adjusting things to mostly usage of enzyme and related tools in Julia with our first talk by Webhub on Optimization.jl.
Thanks, Alex. So, yeah, I think my talk is probably going to be quite short and something most of you already know most about. So, my primary aim here is to present this package in Julia, Optimization.jl, that I've been working on for a couple of years now, I think. But I wouldn't say it's a very mature package yet, but I think the direction we are taking is going to be very interesting for a lot more problem classes that you can probably deal with in the existing software. Cool. So let me start off with right at the basic, right? What is an optimization problem? I think nowadays, especially with the machine learning wave and everything, everyone's kind of familiar with the broad idea of what optimization is. It's about minimizing an objective, right? But when you go out and you'll start looking at problems outside the domain of just having a neural network and training data, the classes of problems is very, very rich. You can't sort of describe just the F here in a very like if you're used to thinking in terms of algebraic languages, for example, you tend to have these large variety of structures that you can impose on the kind of objective that you're dealing with, which is the f, and also the constraints, which are probably just g and x in the slide, right? And why does that matter? Well, it matters because it makes your problems go from exponential solve times to linear or quadratic. Like, just by knowing the structure of the problem, you can basically make decisions for the solver that you use and the way you do the intermediate computations, and it has a very large effect. Right. So what forms as one of the basics of these problems are something called as the oracles, right? This was introduced by Nemirovsky and Yudin in '83. It's nothing fancy. It's just the functions that describe your problem, the objective and the constraint functions, as well as their derivatives, which is usually just the gradient if you're doing first order optimization, but especially in terms of constraint optimization, non-linear constraint optimization, you tend to need the Hessian as well, and specifically the Hessian of the Lagrangian. So I guess it provides a very important class of problems where higher order derivative, specifically second order derivative, becomes essential, right? Which is probably not the case when you're dealing with just simple machine learning optimization workflows. Right. So I briefly mentioned about most of the software that used to exist is either with the practitioners of machine learning or this community of trained optimization people that built algebraic software. By algebraic, I'll show you an example, but basically what you can think of it as, instead of defining these programmatic functions, you build up the problem constructively with predefined functions and sets. And why does that come up? Well, it's basically based on the way optimization theory is taught and thought of in these discrete classes of problem types, which is, at the probably the highest level, you can think of them as convex versus non-convex problems, and like all the theory that all the nice papers that are written and submitted are all for this good and nice class of problems called convex problems, whereas anything that involves machine learning or the more traditional use cases of optimization in engineering, which is basically like something like optimal control, most of the problems there tend to be non-convex, and you can't represent them in those nice structures. You have to basically allow the user to write arbitrary code. Good. So I hope this was sort of motivating in terms of understanding that there is an actual impact of the software that you use on the kind of problems that you can deal with, right? So I've just listed out a few popular optimization frameworks. I guess CVXPy is probably the most famous one. A lot of you might have heard of it. But basically the point I'm trying to make is traditionally this has been thought of as through this model approach, where you basically associate the solver and the rest of the problem definition. Like you associate the objective function and the constraints with the solver, and those are not like two independent objects, which is what I think is the more natural way to think about these problems. And it has been done in the past, but as you can see, this is something I actually wanted to point out. So the comment I made before about the people having a background in optimization, being trained in optimization, building software for kind of that community, versus people just machine learning people or optimal control people just going out there saying, I have this program that outputs some scalar, that's my objective, I don't care about anything else, and I just want to run a gradient based optimizer for it. So you can see this divide happening just in terms of the software that's listed out. So here at the top you have CVXPy, Jump, Drake. Well, Drake is probably not, it won't follow what I'm going to say next, but it does follow. I think it's mostly because of its C++ origins that it has to follow this syntax. But when you look at software that's developed more for the engineering users and for machine learning practitioners, those tend to follow this kind of a syntax where you can independently define. So this includes Cafati and Octax, which are probably the two most popular ones, and obviously SciPy, which is kind of mediocre at everything. So yeah, so what does Optimization.jl look like? Well, I've been talking about the functional and algebraic representation of these programs. Here we are trying to accommodate both approaches of defining those problems, because as I said before, right, optimization problems in theory, and if you are someone who's trained in optimization, you can rewrite it and it can arise in a very nice structured form. So you definitely want this algebraic ways of representing, because you can also use that information to further improve how that problem is actually solved, right? Like you can extract out the structure of the problem in terms of whether, if it's just a quadratic problem or things like that, and then you can use that to make choices of the solver you use, as well as any intermediates that you calculate for that problem. Whereas, if you're trying to do train a neural network, you probably just want to define a function and just throw it with an automatic differentiation backend at Adam, for example, right? So yeah, I think hopefully this two ways of writing out similar problems make sense to you. Cool. So why? Okay. One more thing that I wanted to mention here is this part where you see I'm defining this optimization function that takes the second argument as AutoEnzyme, which is basically this modularized approach to being able to plug in different automatic differentiation backends. Because I mean, everyone here knows there's trade-offs between what kind of automatic differentiation package you use, especially let's imagine if you're dealing with just an objective, you always want to do reverse mode, for example, but sometimes you would have maybe like a multi-objective problem in which you actually have a lot more output from the objective, so then you might want to do a forward mode of differentiation. Cool. So why do we like Enzyme? Why is it an option? Well, Enzyme has this promise of being very fast. It's working at the LLVM level. It should be able to do a lot more optimization of the code, right, to make your optimization problem faster. And the other thing that I just mentioned, having both reverse and forward mode in one package is very beneficial to us, especially like one of the cases I already mentioned, but then also when you're thinking of higher order derivatives, especially like if you're doing the Hessian, you want to be able to do like a forward over reverse, for example. And so like in a lot of packages which only implement one of those modes, you have to actually compose two different packages, and getting automatic differentiation packages to work with each other is a nightmare. So it's quite useful to have both modes implemented in one software. Then yeah, I think GPU compatibility is going to be a big win for us. We have already so we recently did a project where we did use Enzyme on GPUs, though it was I would say it wasn't like the oracles generated from the package were not used. There's some issue with that still, but yeah, we were able to sort of demonstrate an example of it being possible. And in the future, it would be very useful to be able to have an end-to-end embeddable code, which is something that's very essential for optimal control kind of tasks. Cool. So that was the motivation. Has there been any proof of that? Yes. So we have this benchmark problem called the CLNL beam problem, which is on our benchmarks in SciML benchmarks, and you can probably see, right, there's actually like I would say there's two things to notice here. One is that Enzyme is winning over the other Julia optimization packages, being forward diff and reverse diff, right? But this should probably not be here on this plot, but I also wanted to acknowledge how far away we are from state of the art. So the line that you see at the bottom, that's jump. That's one of the algebraic representation of optimization problems like one of the frameworks that does an algebraic representation of the optimization problems. So that's like exponentially better right now. But I would say this is more representative of the time spent in recognizing this structure right now than actually carrying out the derivative functions. So it's not a very fair plot. Like you could probably like split out the problem building and make a, but an end user is going to see this difference. So that's what I've kept it. So you can, just to get an idea of what the problem is, it's scaling. So on the x-axis you have the ends, which is how the problem is scaling, right? It's scaling with 3 into n variables and 2 into n constraints. So it's pretty it's a very useful problem for benchmarking. Cool. What are some of the nice things you can do, right? So these algebraic frameworks that I mentioned earlier, again, are limited in terms of the kind of problems you can solve, machine learning being an obvious one, but also something more, even more complicated, right? So nowadays, doing scientific machine learning is something that's become very popular in engineering domain. What that basically means is, with your engineering model, you also have a machine learning component. So now you're talking about taking derivatives through a differential equation solver, as well as the differential equation being not just composed of this trivial arithmetic, but also have an embedded neural network in there. So so Optimization.jl is used as the optimization library, I guess, for SciML ecosystem, and I'm just trying to show you a couple of wins for us. So this is probably this had a bit of popularity. This was neural ODEs being used for modeling binary black hole orbits, and yeah, it's one of the things where we are able to use optimization. The plot there is that's a project that I was actually personally working on. This is a universal differential equation trained on I don't really know how to pronounce it, but this is like a set of equations that describe a general set of equations that are used to describe different type of neurons, and you can basically see that like extrapolating well and everything, and like underlying, it's the package that we have been talking about. Cool. Then, so I think all the things that we discussed so far, that's something you might have seen already somewhere or the other. But I'm trying to also argue for the fact that making this API so much, making this API sort of decoupling the API between the derivative oracles and the solver has a lot of benefits. One of them being, so recently we added a feature to basically do Riemannian optimization with the same framework. I'll just show you the code in a second. And yeah, so it's kind of cool that you are able to just add on these wrappers on top of all the functions that you are generating, and then be able to do even more cool stuff. Okay. So yeah, I just have I have one example that I am showing you different in different with different solvers and also as a Riemannian optimization problem. So it's the Rosenbrock problem. That's the problem that's on the home page of Enzyme for showcasing their differentiation. It's probably something that we all know. Cool. So just the first thing that I did here, I was able to just use Adam, which is this optimizer that arises out of the machine learning community, not something that is used outside that, but you can use that on the Rosenbrock problem, get a pretty good estimate. But then you know, someone who's trained in optimization would probably want to use something like BFGS instead. And you don't really need to redefine the problem, you don't need to change the interface or anything, you can just call that with the BFGS solver, and you can see the results there. Again, you can go for a higher order method as well. You can run Newton without redefining the problem, and you just like immediately get a pretty good result. You can do constraint optimization with, and oh, by the way, I have been using Enzyme this whole while, right? So I hope that's interesting to you. Yeah, so I can just define the nonlinear constraint, which is I'm saying basically I'm constraining my variables to be on a circle, right? On a unit circle, and then I can run the optimization problem with IPOp, which is this constrained interior point optimizer implemented in C++, and we interface to that with the MathOpt interface package, which is developed by the Jump people. So yeah, that's pretty good. You can see the constraints are almost exactly satisfied. And then similarly, you can define a Riemannian optimization problem in exactly the same interface, and yeah, you get the solution there. This is kind of boring because I'm just using it on the R2 manifold, but the example I had planned was on this symmetric positive definite manifold, but it used to work, but as of yesterday, it doesn't work with Enzyme anymore. So I need to figure that out in the hackathon, I guess. So yeah, that was the examples, and there's a lot to do. There's like a ton to do still. There's obviously you know, when you talk about optimization, especially constraint optimizer, all the performance that comes is from the sparse, generating sparse Hessians, right? I haven't been able to get Enzyme to work with sparsity, but I was told by Billy earlier today that there is a documentation that's going to get added for supporting sparsity in Julia, so very excited about that. Then working with automatic differentiation in general is very frustrating, I would say. And in Julia at least it's, I guess, even more frustrating because there are so many choices. If you are working in JAX, for example, I don't think you need to care about making choices and all of that. So I'm kind of excited about this project that a collaborator has started called differentiation interface.jl, which is basically aiming to put together a ton of different automatic differentiation implementations into the same interface which can be reused across packages. So hopefully, but well, it has a long journey to go as well. I still don't have sparsity, so I doubt they will for a while. So yeah, that was it from me. Thank you.
Thank you. Any questions?
So when you're solving a bi-level optimization problem or a mini-max problem, there's this temptation to sort of call the optimizer within the function that you're seeking to minimize or maximize. You know, rather than sort of recast the problem in a way that maybe was more friendly to the optimizer. If you did that within your framework, would that work? Can Enzyme differentiate through the optimizer itself?
Yeah, so the question was, if you have a bi-level optimization problem, does Enzyme work with that, right? Because there is this, there's a choice you have to make there in terms of basically caching the problem or like redoing it completely. I have not I don't think I've tried Enzyme with it. We have solved bi-level optimization problems from the algebraic interface that I showed you, and there the caching story is sort of more in place. I don't think I've tried Enzyme with that, but I would be very suspicious it will work. my code is bad. I'm not blaming Enzyme, but yeah.
So my guess, and I'm not sure if this is implemented, but like in a lot of places recently in sort of the Julia ecosystem, if you have some sort of high-level structure, right? Let's say you have like a linear solve, or in this case, right, you're solving for a minimum of something. You can define a custom derivative rule, and then usually you can have that custom derivative rule itself call enzyme on the inside. So like if you're differentiating an integrator, you can like say that is integrating the derivative of the inside subject to various sorts of constraints. My guess is probably that if there were such a rule, that's probably what you want to use, and if there isn't such a rule, that's probably also what you want to have, and then that would be a way of resolving it. There are already some of those inside of, say, like the linearsolve.jl package that allow that specifically allows Enzyme to avoid doing a redundant computation of the LU decomposition for both the forward and reverse pass. Again, the specifics here will depend on exactly the code that you're dealing with, but my guess is something like that might be the.
So there is actually rules that you can write. There has been this great work by people from Stanford, at least for, again, convex problems. So there are these adjoints that you can basically define for an arbitrary problem given if you know the solver that you're going to use for it. So that would probably work out quite well. But that's not something we have implemented yet.
And the question is kind of tied back to the first presentation, a question of, is your ecosystem kind of closed?
Right.
Can you sort of...
So I would say it's closed modulo, you have to write rules. Right? So yeah, that's probably the shortest answer I can give.
Other questions?
Sorry, it's really a very naive question. You're connecting Optimization.jl to the differentiation tool, but another perspective would be that you don't care about where your gradient and your cost function evaluation comes from. You just, wherever you get it from, and it could be from a very large scale code and its derivative code which provides a derivative, then you provide that as an input to the optimizer. Is that something that you can do or that you're looking to do?
Yes, so that, yeah, sorry. So the question is, there's an argument to be made about not caring about where the derivatives come from at the solver level, right? I think so I would say that's exactly what I'm trying to motivate with my design, is that you don't need to, so let me try to give some context, right? A lot of, the most state-of-the-art solvers, these are written in like C++ or Fortran, right? Like every other numerical software out there. So they do tend to have their own routines for calculating the derivatives and stuff like that. And they would be using finite difference in there, right? So what I'm actually arguing for is this decoupling, that the solver doesn't have to care where the derivatives are coming from. I'll just generate them for you automatically. I'll have just these functions, which are just nothing more than Julia functions, that you can basically call inside your solver and get supposedly, the most efficient way of calculating those derivatives.
But I don't want it to be called inside the solver. I want it to be separate from the solver.
Well, then the solver is just taking this function as an argument and evaluating it at the current iterate, if that makes sense.
I want the evaluation of the function and the gradient separated. And then I want basically just to provide this to the solver and then choose whichever LDFGS or whatever optimization provides to me. And it may be suboptimal, but...
I don't think I get that. Like, what do you mean by have the...
So, okay, the iteration, of course, has to be governed differently, right? But what I don't want is to have the function call, because could be very complex, could be by a very complicated, large-scale geophysical model, for example.
Yep.
Plus its adjoint, which would be generated using Enzyme, but it would again something be separated. I want that to be kind of decoupled from then the application of the, let's say, the LDFGS method.
Yes.
Or
So again, that's exactly what I'm.
So
Yeah. So you still need to be able to give LBFGS or whatever, like the solver, a way to calculate the derivative at the current point, right?
That's right.
So I just provide that function to. So how does that function calculate the derivative? The solver doesn't need to care about that at all. For them, it's like a black box. It's like the definition of an oracle is this black box that just, if you give it the current input, it gives you the corresponding. Yeah, sure. Yeah,
Okay. Yeah, you said it was a short talk. You're exactly on time. Thank you.
We need to take 2 minutes before.
Okay, so our last talk of this session is by Kai talking about Turing.jl, keeping in Julia land. Please.
Hello everyone, I'm Kai. So this, again, could be a short talk. So I will start with...
Probably will not be.
I'll start with like a simple introduction to Turing and why we need automatic differentiation, and talk about some recent integration of Enzyme with Turing and some benchmark result Tor and I get yesterday. Right. So what is Turing? So Turing is basically a general purpose programming language, meaning that you could write programs with some probabilistic semantics. The main purpose is to using them to represent some graphical models and do inference on them. And Turing is fully implemented in the Julia programming language. We started the project since 2016 or 17. It's been a long journey. And the design principle is to make it very approachable to like actual practitioners who will do Bayesian inference. Those are users actually already familiar with MATLAB, Python, and R, and or other programming language like Stan. And Turing has been growing popularity in the past few years. So this will be like a typical Turing program looks like. You basically have we have this tilde notation that allow user to define like which kind of probabilistic distribution a particular variable follows, and the user can define a generative process, a forward process of how the observation, which will be the actual data, actually be generated. Then they can choose to have this model conditioning on a particular observation they collect from either experiments or other stuff, and the Turing can do the inference for you, meaning that given the data, what actually the distribution of those latent variable looks like. So, like again, as we designed Turing to be actually used by practitioners, there will be a lot of papers that outside our Turing team have been using Turing to do all sorts of topics from biology, economics, all kinds of science topics. So why we need automatic differentiation in Turing? So as I said, the main thing Turing automates is to do Bayesian inference for you. And there are a lot of Bayesian inference algorithms. But in our context, we're mostly treating Bayesian inference as a sampling problem. Like as long as you can sampling from the posterior that your model and data defense, that's what we call that's what the main thing we're automating. And there are a lot of Bayesian inference algorithms. They are simulation-based, which you kind of run the program multiple times and get a sense of what's the posterior look like. But there are also those evaluation-based, where you kind of assess the potential parameter at different location and trying to use that to get a sense of what's the posterior look like. And the most popular or most widely used algorithm is on the evaluation-based, which is called Hamiltonian Monte Carlo. Basically, the idea is that if you can use the underlying geometry to do the sampling, you can sample more efficiently. And when it comes to the practical implementation, our Turing DSR, which is those tilde notation that define latent variable I just showed you, they basically transform the whole program into a function that you can evaluate the log density at any given parameter, any point in the parameter space. And for HMC to use the underlying geometry information, you need to take the gradient of that function with respect to the parameter. And that is actually the main computation happens when you do HMC. Like each sample requires 10 to 1,000 evaluation of that gradient. And to make a kind of sensible inference, you usually need more than 1,000 samples. Okay, so we've been playing with different AD backend. Originally, we had forward diff as the default, which is still default now because a lot of users actually work with very low dimensional problems as a starting point. But we have been supporting Zygote, reverse diff, and I guess, yeah. And currently in this PR that, let me actually open it. We have the initial enzyme support. So you can see that this PR actually opened quite a long time ago, which is still not merged. So it kind of has opened like when enzyme start get some popularity, but it haven't been kind of have any progress for a long time. But it kind of picked up in mid-January last year, and William and David and Tor have been working on this PR. I think it's currently at a state where there are quite a lot of models that are already working with enzyme. Let me go back to this. Okay, so I'm going to show, discuss two particular models, like how their performance with different AD backend and why the reason there's a difference. So the first model I would like to kind of discuss is this item response model, which is your data is like different user purchase different item or not, and you want to use that to infer the user's preference as well as, I guess, items popularity, and that might be useful to recommend new item to users, so on and so forth. So this, again, naive, because there's a reason we call it naive, because we have optimization, which I show you later. But you can see, we're basically saying each of those parameters are independently from some Gaussian distribution, and for each observation, which is whether or not a particular user purchased a particular item, it follows a Bernoulli distribution, and the parameter is just a soft sigmoid between the difference of the item and the user. So as you can see, there's a loop here which kind of makes some AD backend quite slow. So this is a benchmark where we varying the number of dimension, which is how many items are there, which is effectively the dimensionality of the latent space we're sampling. And that's the x-axis, and y-axis is just the actual time to do a particular sampling run in milliseconds. And as you can see, enzyme is very efficient in this case, and the second efficient one is actually reverse diff, which with compare tape, and again forward diff works kind of great in low dimension but scale poorly when dimensionality gets high. And there's this Zygote, which is kind of the thing we notice at Turing, where Zygote is generally underperformed. And our guess for that's why it's happening is because the particular way our DSL works by how it decomposes or translates the code into the model code into Julia code. We have a bunch of if statement on whether or not that variable is actually visible or given or it's latent, and it will do different operation on it, and it kind of introduce type state instability when Zygote is getting the gradient. So again, this is the same result, but what we're plotting is what's the ratio of gradient computation versus only the forward evaluation. As you can see, or most of dynamic latencies we are dealing with. And one dimensionality is low forwarding actually. The actual computation takes over the overhead and the overhead diminishes. So what I show is two cases that enzyme currently working nicely as models, but we also, while we were working on this benchmark yesterday, we found that some more edge cases. There's one particular this truncated notation from distributions.jl, which you can truncate any distribution to like have an upper lower bound, and somehow enzyme breaks in this case. We haven't, deep diving into this yet. But again, there's still some work to do to make like things work more smoothly. So what's next? I think on the enzyme side, we kind of collect a few more edge cases. Probably we can work together to share like detailed trace see how can fix them. And there's this interesting point I bring up during that manually optimized example that seems that there's some room on terms of actual code optimization on the enzyme side could be done that to make those versions which you could manually optimize more efficient. And on the Turing side, we kind of be step away from mutation, or at least we support, but we don't always encourage people to use it because it's not compatible with all ADs. But since enzyme is very promising in this case and could potentially be our next default AD, we could potentially encourage users to use more. And as said, we will try to figure out more edge cases or failure cases that we can work together with the enzyme team to make the whole integration better and give a more smooth experience if we switch to enzyme as a default AD on the Turing side. Great, yeah, that's my part. Thanks for listening, and special thanks for everyone contributing that here, and also people who actually make those slides.
Any questions?
Yeah, so I have two questions. One of them is, I guess, pretty high level, which is, do you have an intuition for when enzyme performs well, when it performs maybe slightly less well?
Can we stop on that and you can repeat that?
The first question is when enzyme works better than other AD backends. So I don't have a very conclusive intuition, but from what we've been seeing, it seems that it seems that enzyme works better than other AD in most of naive Turing implementations, meaning that you don't do any specific optimization to just translate Turing code into, say, simple vectorized mode or vectorized operation or matrix multiplication. And I guess that's where enzyme seem to be consistently outperforming. But once we do some sort of manual operation, it seems that other AD, as this case showing, in particular mode can still outperforming enzyme.
Okay, and then my second question is about that truncated distribution example with the slide, the truncated distribution. So I couldn't quite see, are you differentiating with respect to the truncation parameter, as in varying the location of the threshold?
No. So second.
Sorry, repeat the question.
Yes, second question is about this truncated failure case, whether or not we actually differentiate through the truncation parameter at all. The answer is no. We actually, this truncation parameter is a constant. What we are differentiating is still the variable itself, but somehow we get a segmentation fault in this case.
Okay. Yeah, I was just curious. Thank you.
Yeah.
Any other questions? Please.
When you're showing that enzyme has some overhead, are you including also compile time of enzyme to compute the derivative of this time?
No. So the question is whether or not we compute the compile time. We definitely get rid of the Julia compile time.
No, enzyme.
Yeah, maybe not. I'm not very sure. Yeah.
Any more questions? No, then let's thank Kai again. This is the end of this session, and we have a coffee break until 4 p.m. Eastern Time, so we have 40-ish minutes. Coffee has just arrived, thanks. And we will be back in 40 minutes.